Welcome back, everyone, to the deep dive. I've been getting a lot of messages from you all asking about holograms. How do they work? How are they made? And I'm excited to say, well, today we're going to do a deep dive into that very topic.
Yeah, those shimmering rainbow effects are everywhere, right? Like you see them on everything. Gift bags, credit cards, even those little security stickers. It's kind of wild when you think about it.
It is. I mean, you see these holographic images and it's like, whoa, how'd they do that? So to really understand this stuff, we're going to be looking at this research paper. It's called Acquiring Spatially Varying Appearance of Printed Holographic Surfaces.
Catchy title.
Right. And the paper is super cool because it actually lays out not one, but two different methods for capturing and then recreating these holographic effects. Like, how awesome is that? Two different ways to decode those holographic secrets.
Yeah, that's what makes this paper really interesting. Two different techniques, both with their own advantages.
Exactly. Before we jump into all of that, though, can we just take a step back for a sec? I think it's good to start with the basics. Like, what exactly are holographic surfaces? We see them all the time, but what's the science going on there?
Right, they're becoming so common that it's easy to forget how complex they actually are. At their heart, you've got these surfaces covered with microscopic patterns, these things called diffraction gratings. They're kind of like tiny prisms, but instead of being 3D, they're just one-dimensional.
Okay. Tiny prisms, but flat. So what do?
Well, they do what prisms do, right? They split light into its different colors. But the cool thing is they're arranged in these super intricate patterns, and that's what creates the holographic effect.
So these microscopic gratings, these like flat prisms, they're responsible for those amazing rainbow effects.
You got it. The way they're arranged, the spacing between them, all of that determines what kind of holographic image you're going to see. So when you look at those complex, shimmering designs, that's all thanks to those tiny gratings and how they're messing with the light.
That's incredible. When I was reading the paper and it talked about capturing and recreating those effects, it made me think of like those crime shows where they're analyzing fingerprints.
Oh, yeah, I can see that. Except here we're dealing with, light instead of fingerprints, and the patterns are microscopic.
Exactly. So how about we dig into that first method they talk about? I'm curious, how do you even start capturing these holographic properties?
Well, the first method, I gotta say, it's shockingly straightforward. You wouldn't believe how simple the setup is. They were able to do it with just a smartphone flash and a DSLR camera.
Wait, seriously, they're just taking a picture. That's all it takes.
Essentially. The flash illuminates the holographic surface, and the camera, the DSLR, captures that diffraction pattern.
Hmm.
All those crazy colors and the way they're spread out.
So they shine the light on it, take a picture,
Yeah.
and then
Then the fun begins. By analyzing that photo, looking at where the colors land and how bright they are, they can actually work backwards and figure out the orientation of all those little gratings, like how they're tilted and how far apart they are.
hold on. So just by looking at a photo, they can map out all those microscopic patterns. That's crazy. Does that mean like anyone could do this at home?
Theoretically, yeah. I mean, for basic repeating holographic patterns, it's definitely possible. That's what's so cool about this method. It makes it much more accessible to analyze these surfaces. You don't need a, fancy lab or anything like that.
That's amazing.
Yeah.
But wait, what about those holographic surfaces that don't have a simple repeating pattern? I know you mentioned that the paper talked about that too. What happens then?
That's a great question, and that's where that second method comes in, the one we talked about. It's called polarization imaging, and it's how they capture those super fine details, even when the holographic pattern is continuous and doesn't repeat. Think of it as like upgrading from standard definition to, ultra high definition.
Ooh, polarization imaging. Okay, that sounds super high tech. What's the basic idea behind it?
It's based on the idea of polarized light, kind of like what those 3D glasses you wear at the movies use.
Okay, I can kind of picture that.
Yeah.
So how does that help us understand holograms?
Well, they used an LCD panel for their light source because LCDs naturally emit polarized light. Then they converted that light into circularly polarized light. It's basically like twisting the light waves into a spiral.
Circularly polarized. Wait, hold up. How do they do that? Twisting light.
They use something called a quarter wave retarder. It's a special filter. Think of it as forcing those light waves to like vibrate in a spiral pattern instead of all over the place. And this spiral allows them to see how the light interacts with the holographic surface in a very specific way.
So it's like they're giving the light a special tool to interact with the surface, right?
Exactly. Then they take a bunch of images, rotating a polarizing filter as they go.
Rotating a filter.
Because by doing that, they can see subtle changes in how bright the light is in each image. And those changes, believe it or not, tell them the orientation of those tiny gratings, even in the most complex surfaces. It's mind-blowing stuff.
So basically, this method is like our high-powered microscope for those super detailed, non-repeating holograms. And that first method, the flash one, that's like our everyday tool for simpler surfaces.
That's a perfect way to put it. And the really cool part is these techniques, they're not just for recreating those pretty rainbow effects. They can be used for so much more.
Now that you mention it, what else can we do with this stuff? It sounds incredibly powerful.
Oh yeah, the applications are huge. Think about like quality control for a second. Like imagine you're trying to check those holographic security strips on, say, a credit card or a banknote. You need to make sure every tiny detail is exactly right?
Yeah, that makes sense. Those things are designed to be really hard to counterfeit.
Yeah. Exactly. And with these techniques, you can actually spot those tiny imperfections that, the human eye would never catch. It's like having a microscopic eye to ensure everything is perfect.
Wow. So it's not just about, like, understanding how holograms work, but also about using that knowledge to make them even better and more secure.
Exactly. And it goes beyond just security, too. These methods are opening up a whole new world of possibilities for, like, artistic expression with holography. But before we get to that, I'm kind of curious, would you like to actually see these methods in action? See how they work on real holographic
Oh,
surfaces?
absolutely. Seeing is believing, right?
Right.
I think that would really help to bring all of this together.
Okay, cool. So let's start with an example using that flash illumination method. The researchers, they analyzed a holographic gift bag, the kind with like a repeating pattern of stars on it.
Okay, so like a simple repeating pattern. I remember you mentioned that because the pattern repeats, they only needed to analyze like one tile of that star.
You got it. They just took a picture of that single star using, the flash and DSLR setup. And from that one photo, they were able to create this amazing map of how all those microscopic gratings were oriented within that star. They actually used like color coding, so each color on the map represents a different grating orientation.
Wow, so like a rainbow roadmap for how the light is interacting with that star?
Yeah, that's a great way to put it. And get this, they could actually use that information to like digitally recreate that holographic star. And the rendering matched the actual holographic effect on the bag, almost perfectly.
That's incredible. So they're basically like reverse engineering the whole visual effect. It really shows how powerful even that simple flash method can be.
It is. But they didn't use that method for everything. For more intricate designs, the ones with a lot of detail, they had to use that polarization imaging method. One example that really highlights this is a holographic SIGGRAPH logo, like from a conference badge.
Oh yeah, those logos are usually pretty small and pretty detailed, right?
Exactly. And all those fine lines and curves, it basically ruled out the flash method. So they used the LCD setup with the quarter wave retarder and all those polarizing filters to capture that level of detail.
Wow. And they were able to map out those tiny gratings on such a small surface.
Yeah. It's pretty amazing. They created a high-resolution orientation map of the entire logo, capturing every single curve and every little fine line.
That's insane. Okay, so they can analyze both simple and complex designs. But, there was one type of holographic surface we talked about earlier that I'm still kind of curious about, the stochastic ones.
Oh, yeah. The ones that look, totally random.
Exactly. I mean, how do you even begin to analyze something like that?
Well, those are definitely a challenge because there's no, like, repeating pattern to latch onto. It looks like someone just sprinkled those little gratings all over the place with no rhyme or reason.
It's like organized chaos, right?
Right. But the researchers, they figured out that even though it looks random, there's probably some kind of underlying rule, some kind of probability distribution that governs how those gratings are placed.
Okay, so instead of looking for a specific pattern, they're trying to understand the rules of the randomness.
Yeah, that's a good way to think about it. So to figure this out, they actually used the flash illumination method, but with a little twist. They captured images of the diffraction pattern, but they used a green spectral filter. Basically, they were only looking at one specific wavelength of light.
A green filter. Why'd you screen?
It's kind of like tuning your radio to one specific station. It helps to cut through all the noise. By isolating that single wavelength, they could see the signal, so to speak, within that randomness.
Did they use that filter to kind of like cut through the chaos and see what was really going on? Did it work?
It did. They were able to figure out the statistical distribution of those gratings. They basically uncovered those hidden rules. And using that, they could actually recreate similar stochastic holographic effects in their renderings. Pretty cool, huh?
So even in all that apparent randomness, there's still an underlying order.
That's really fascinating. It sounds like we're just scratching the surface of what's possible with holography.
Oh, absolutely. And this deeper understanding, it's opening up all sorts of incredible possibilities, especially when it comes to like using holography for artistic expression. You want to dive into that a little bit?
Definitely. I mean, we've talked a lot about the science. I'm really curious to see how they can actually use these techniques, to create some cool art. So how they actually use these techniques, to create new holographic art. Do they have to like invent a whole bunch of new tools and materials? That's the coolest part. They didn't have to reinvent the wheel or anything. They were really clever about it. They focused on manipulating the data they'd already gathered. All that info about the arrangement of those little gratings. Remember that holographic gift bag with the repeating pattern of circles?
Yeah, yeah. The one they analyzed with the flash method.
Right. So initially, that bag, it had what they call a constant periodicity. Basically, all those gratings were spaced the same distance apart, which created a, pretty standard rainbow effect around each circle.
Okay, so like a simple halo of color.
Exactly. But then they got creative. Instead of keeping the spacing the same everywhere, they started introducing some variation, like making the gratings closer together in some spots and farther apart in others.
Ah, so they're kind of like creating a new blueprint for how those gratings are arranged.
Precisely. They made this new periodicity map, and then they used that map to guide the rendering process. And it led to some really cool dynamic effects. Like imagine those same circles on the gift bag, but now the rainbow shimmer, it changes as you move the bag around. The colors shift and like flow almost like a wave of light.
Whoa, that's way more interesting than just a static rainbow. So just by adjusting the spacing of those tiny gratings, they could completely change how the whole thing looks. That's wild.
Yeah, it's like they're composing music with light.
Yeah.
And they tried out a bunch of different ways to vary that periodicity. There was something they called a quadratic blend, where the spacing changes gradually across the surface, and a sinusoidal blend, which creates more of a, wave-like variation.
That's really cool. I mean, it just shows you when you understand the science behind something, it opens up so many creative possibilities. But even with all these advancements, there's got to be some limits, right? Like, what are some of the things we still don't know about holography or the challenges that are still out there?
Yeah, there's always more to explore. I mean, most of what we've talked about today has been focused on those single-layered holographic surfaces, the ones with just that one layer of those tiny gratings. But a lot of the holographic designs you see out in the world, those are multi-layered, meaning they have, multiple layers of gratings stacked on top of each other.
Oh, wow. So like multiple layers of those diffraction gratings, I bet that creates some even crazier, more complex effects, right?
Absolutely. But it also makes it a lot harder to analyze and recreate. We've made a lot of progress with single-layered surfaces, but multi-layered holography, that's still a big frontier.
It makes you wonder what kind of amazing visuals we'll be able to create once we, really crack the code of those multi-layered designs. It's pretty exciting to think about.
It is, and that's what's so great about research like this. It not only gives us a deeper understanding of, how things work, but it also sparks our imagination. It shows us what might be possible in the future.
I totally agree. It's been an awesome journey exploring the world of holography with you. I feel like I've learned so much about, how those mesmerizing visuals are created.
Me too. And hopefully this has sparked your curiosity to keep learning and exploring. Who knows, maybe you'll be the one to make the next big holographic breakthrough.
Maybe. Well, thanks for joining us on this deep dive. Until next time, keep looking for those hidden wonders, because you never know what you might find.